Yes, so thanks everyone for coming to a new edition of this Talent Q seminar. Yes, so today we're very happy to have Ainesh Bakshi as a speaker. So Ainesh, well, he started as a assistant professor at New York University in New York, of course. And I understand that he's trained as a theoretical computer scientist. But I think in the past few years he's been getting a lot more into quantum information, quantum computation, and also quantum many-body physics, where he's actually been getting a lot of interesting contributions in the field, and very interesting also in the intersection of, let's say, both classical and quantum algorithms for many-body systems, and for learning, and for things having to do with temperatures and with classical and quantum algorithms. And really, I think he and his collaborators are exploring a very nice intersection of quantum many-body physics and also, computational complexity and complexity of classical and quantum algorithms. And then today he's going to tell us about, in particular, the structure of entanglement in many-body systems when they have a temperature, and in particular in spin chains. And with that, please, Ainesh, the room is yours.
Thank you so much for that lovely introduction. I'm indeed a theoretical computer scientist, but I'll be telling you things about entanglement in quantum spin chains today. Feel free to stop me at any point and ask for clarifications, or if you have questions.
Yeah, so maybe just a comment. If people have questions, maybe you can write them in the chat, and I will be paying attention and relay them to Ainesh. And then at the end, there's also time for questions. Yeah. Sorry.
Okay, awesome. So today I'll be telling you a bit about how to quantify entanglement in spin chains. These are 1D Hamiltonians at any temperature, and this is based on joint work with Soonwon Choi, who's a professor at MIT, and Saul Pelatowski-Cameo, who's a PhD student there. Okay, so let's get started. And I like to start talks by first saying what the overarching research direction of the talk really is. And the motivating question behind this work is, how do we make progress on quantifying entanglement in thermal states? So here we're thinking of our quantum many-body system already being at thermal equilibrium. So it's not a dynamic process, but we're already at equilibrium. And as we vary temperature, we're interested in understanding how entanglement behaves as you increase or say decrease temperature. Okay, so that's the very high level version of the question that we're interested in. And the first thing that you might ask when you see a question like this is, why should we care? Like, why do we care about entanglement in thermal states? And one reason for that, I'm sure you know many more applications than I do, but one reason for it is that entanglement enables interesting tasks that are otherwise impossible. And these tasks range across a variety of areas. You can have tasks in quantum sensing, where you really require entanglement to make precise measurements. Um, Other tasks that are enabled by entanglement are things like quantum teleportation. You can use it to understand the phases of matter, maybe topological phases of matter, which I don't know much about. Something that is a bit closer to home is understanding quantum advantage. So what are problems where you can get efficient quantum algorithms and you do not hope to have efficient classical algorithms? And quantifying entanglement is sort of necessary for quantum advantage because this is, in some sense, the only distinction between quantum and classical algorithms. Okay, so with that motivation in mind, maybe we can proceed and be a bit more grounded technically. So okay, so how do we define entanglement? And this is quite a hard question, at least coming from a background in theoretical computer science. It took me a while to understand like all the different definitions and how they relate to each other and so on. So let me give you a quick overview, and I'll go quickly for this part. So, and I'm sure people have seen this before. So entanglement for pure states is really well understood. You can define it in many ways. Okay, but let's say I focus on bipartite entanglement for now, and I look at my system for the purposes of this talk. Our system is just going to be a 1D spin chain, and I split it up into two parts. The left part is A, and the right part is B. And what I would like to do is just measure quantum correlations across this cut. Okay. So how do we be a bit more precise about measuring quantum correlations? Well, we can look at the state. Think of the state for now as being some pure state. And if this pure state can be written as a product state, which means you can write it as the tensor product of something acting on the A subsystem and something acting on the B subsystem, then this pure state is separable. And if it doesn't admit this product decomposition, we'll say that it is entangled. Okay, so far so good. At least now we've managed to classify the Boolean question of when you are entangled versus not entangled. This is not so satisfying. We would still like to measure how much entanglement there is. Since we were talking about correlations, we would like a measure for like how much are these correlations across the subsystem A and the subsystem B. And even this admits a really nice definition. This definition is the so-called Schmidt rank. And what this says is, okay, maybe you cannot write it as the tensor product of just one state, like on the previous slide. Maybe you can write it as a tensor product of R of them. Okay, so psi admits the following decomposition. It's a sum from I equals 1 to R, lambda I, which is a coefficient, and then AI on the A subsystem, tensor BI on the B subsystem. Okay, and the minimum such R, you can think of it as quantifying how much entanglement there is across this cut between A and B. Okay, and in some sense, this is everything that you'd hope for in order to quantify entanglement in a pure state. And that's why I'm saying it's quite well understood, because any other notion of entanglement that you were interested in, you can derive it from this one. You can relate it back to the Schmidt rank. Okay, so where am I going with this? It seems like pure states are really well understood, but the motivating question at the start of the talk was trying to understand entanglement in thermal states. And thermal states are not pure unless they are actually a zero temperature state. So quantifying entanglement in mixed states turns out to be significantly harder. Okay. But okay, we like doing hard things, so let's keep persevering. And let's try to understand why this is hard to begin with. Okay, so as an example, consider the maximally mixed state on 2 qubits. For me, this means the identity matrix, the 4x4 identity matrix. I'll denote it by rho. And let's recall some definitions. In particular, let's recall the definition of a bell pair. It's written over here on the slide. I won't read it out. Now this maximally mixed state on 2 qubits actually admits two essentially completely different looking decompositions. The first one is a decomposition in the computational basis. It's like a decomposition into product states, and it looks pretty separable. So it's easy to see that this decomposition on the left of the screen doesn't have any entanglement between qubit 1 and qubit 2, since it's just a convex combination of product states. But the same state also admits this Bell state decomposition on the right, and this one looks as entangled as you could get. Okay, so this even two qubit example sort of hints at the difficulty of quantifying entanglement in mixed states. And the way you usually get around such discrepancy in decomposition is that you try to find the minimum over decompositions such that across the cut that you're interested in, you have the minimum Schmidt rank. Okay, so there is a way to resolve this, but at least you get that this is a difficult problem. Okay, so it's not only just analytically hard to define and analyze entanglement in mixed states, it's also computationally hard. So computing whether mixed state is entangled or separable is actually NP hard. And this is an image of what would happen if you try to run an algorithm for this problem on your laptop. Okay, so what this means is we don't expect any efficient algorithm to tell you whether your state is entangled or not. Okay. So with that background in mind, let's actually try to understand thermal states of local Hamiltonians. So I said that quantifying entanglement in mixed states is hard, but we're not interested in arbitrary mixed states. We're interested in mixed states with structure. In particular, today we're only interested in thermal states of local Hamiltonians. Further, this local Hamiltonian will only be on the line. Okay, I want to define it more generally, but I want you to just think of it as n qubits on the line. Okay, so Hamiltonian on n qubits with the nearest neighbor interactions, I'll represent it as this matrix H. It will admit a decomposition into local Hamiltonians. Each of them will be represented by H sub I. And since this is a spin chain, HI only acts on site I and I plus 1. Okay, so I'm assuming that the locality is 2, but everything in this talk will work if you continue to be on a line and your locality is larger than 2. I just didn't want to carry around more notation. Okay, and then the Gibbs state, which is the formal description of the thermal state at any inverse temperature beta, is given by this density matrix, which is obtained by exponentiating the Hamiltonian H. So you look at e to the minus beta H, and you divide it by the partition function. That's just the trace to make this an actual quantum state. And the starting point for understanding entanglement in Gibbs states is the following. So here on the x-axis, I have the inverse temperature, and this is going from 0 to infinity. Okay, and we want to understand how much entanglement there is in these states as a function of inverse temperature, which is beta. Okay, so what do we know about this? We know that if you are at 0 temperature, or if beta is infinity, there exists Hamiltonians whose ground states have long-range entanglement. Okay, so we can show this analytically. We can also observe this in a lab. On the other extreme, we know that if our system is really hot, or if the inverse temperature is really small, then you are separable or unentangled. And this separability threshold was first established in 2003. I mean, it sort of makes sense. Like the convex set of separable states has non-zero measure. So if you make a tiny perturbation around the maximally mixed state, you should remain in the set. Then if you try to quantify how big a perturbation you can make, it turns out that what you end up with is, a temperature or an inverse temperature of 2 to the minus n. So here n is the system size, and if you have n particles, it's saying that if the temperature is less than, inverse temperature is less than exponential in n, then you are separable. Okay. So this is our folklore understanding of quantifying entanglement in Gibbs states as a function of inverse temperature. More recently, my collaborators and I managed to improve this threshold. In particular, what we showed was for any local Hamiltonian, this need not be a spin chain. It could be a 2D lattice, a 3D lattice, more generally even an expander. The separability threshold actually does not depend on system size. And in particular, this Gibbs state, rho sub beta, is separable for any beta less than a fixed constant. So that's beta star C over here. And this constant is actually independent of system size. So what the statement is saying is, no matter what local Hamiltonian you come up with, if you look at the Gibbs state at any temperature less than, or any inverse temperature less than beta C star, it is provably unentangled. Okay, and I do want to point out that Alvaro mentioned that this remark in our original draft is actually more interesting than we thought, and we had to then rewrite the paper to be about the remark instead of what the paper was originally about. Thanks, Alvaro. Okay, any questions so far? Okay, I'll keep going. So the central question that we're interested in today is to understand what is going on in this region between beta star C and infinity. Okay, so below beta star C, we know you're separable. At infinity, we know there's long range entanglement. And we don't really expect entanglement to go from like not existing at all to suddenly every single qubit in your spin chain is entangled, looking like you're maximally entangled or something. So we would expect there to be a smooth transition. It's just that we don't know how to analyze this rigorously or even state how to quantify it. So that's what we'll be interested in doing today. Um, okay, and one thing I wanted to point out was actually we can run some numerics and see that it does have somewhat of a smooth behavior. It goes from being 0 to increasing, but not all at once. Okay. And the way to see this is here's an example. Here's a concrete example. So I have the Heisenberg Hamiltonian on 6 qubits. It's defined over here. And the plot I have is I'm plotting the following. So again, the x-axis is inverse temperature. And the y-axis is entanglement negativity. So this is just some entanglement monotone function. It means that if it's non-zero, then your state is definitely entangled. And if it's 0, then it could be entangled. It also could be separable. All bets are off. And the precise definition of negativity is not very important. It requires taking a partial transpose. But what I'm plotting here is just the negativity between qubits 1 and 2. And if we start off with beta being small, this is the so-called high temperature regime, we would expect that the system is unentangled. There is no entanglement because of the theorem on the previous slide. And as we increase it, we see that there is this emergence of entanglement, at least between the first 2 qubits. And that's what we're interested in. So we're interested in explaining what is going on in like this whole region. Okay. Okay. So if we want to quantify how much entanglement there is in Gibbs states, I should give you a formal definition of what it would mean to quantify how much entanglement there is in this regime. And to define this notion, let's quickly again recall the Schmidt rank. The Schmidt rank was defined for pure states across some bipartition. The Schmidt rank was just a decomposition into R many product states. You can generalize this definition into what is known as the Schmidt number. And this generalization will work for mixed states. And here's what it says. It says that you should look at the fewest Schmidt terms needed when writing rho as a mixture of pure states across this bipartition again. But now minimize over all unravelings or decompositions of rho. Okay, so look at rho being decomposed into any summation over I, pi, psi I transpose. And minimize over all such decompositions. And the quantity that you're minimizing is the Schmidt rank in every pure state in your decomposition. Okay, so this notion is called Schmidt number. It was introduced by Daral and Horodecki in 2000. And for the purposes of this talk and for the paper, we'll use this notion to quantify how much entanglement there is in mixed states. And just as a sanity check, the Schmidt number is 1 if and only if rho is separable. So this is a representative measure of entanglement. A bit more contentiously, in the paper, we try to argue that this is actually the most stringent measure of bipartite entanglement in mixed states. And let me try to defend this position by giving you a couple of reasons, which we'll get to after I state the theorem. But for now, let's just believe that Schmidt number is an important quantity to capture the amount of entanglement in mixed states. Okay. Okay, so let me tell you the main result of this paper. The main result says the following. It says that given any inverse temperature beta and a quantum spin chain H, the Schmidt number of the Gibbs state across any cut. So you get to pick the cut. It could be between the first two qubits. It could be anywhere else. The Schmidt number is at most doubly exponential in beta. Okay, so some remarks about this statement. The first one is that the Schmidt number is independent of system size. So it doesn't depend even logarithmically, say, on the number of particles in the system. So you can take this theorem and you can apply it in the thermodynamic limit, for instance. Okay, so let me say a bit about the consequences, and maybe this will get to the heart of why Schmidt number is such a stringent notion of quantifying entanglement. So there are some consequences you can derive just by the Schmidt number being bounded. The first one is that the distilled entanglement and entanglement cost are the logarithm of the Schmidt number, which is, in this case, exponential in beta. I'm not going to define what distilled entanglement and entanglement cost are. These are more operational notions of entanglement, and they show up in resource theory, but we'll just state that these are bounded. And if you're interested in what these mean, you can talk about it offline. The second consequence is that any entanglement of formation, this is yet another operational notion of entanglement, and it's parameterized by this parameter alpha, which is typically between 0 and 1, 1 giving you the original 1 Neumann entropy. So Renyi entanglement of formation of all orders, including alpha equals 0, is again bounded by exponential in beta. This is another fact that you can derive just from the Schmidt number being bounded. And let me remark that this really cool paper by Kuwahara, Alhambra, and Anshu from 21 also bounded the entanglement of formation. So this paper is about proving thermal area laws, but one of the statements that they prove in this paper is a bound on entanglement of formation. And they obtain a bound for any alpha greater than 0. Their bound has a better dependence on the inverse temperature than us. It's better than exponential beta, but their bound doesn't apply for alpha equals 0. So in that sense, it's sort of incomparable. Okay, so maybe I'll pause here and see if there are any questions about the theorem statement.
Yeah, I think there's nothing so far. So
okay, let's keep going then. So let me tell you another result that we managed to prove in the same paper. This is going to be related to this claim that entanglement is strictly finite, but it's going to give you a more useful decomposition. Before I state it, let's recall the definition of a matrix product state. So an n-qubit state psi is a matrix product state with bond dimension chi. If it can be written in the following way, it emits this decomposition into sum over bit strings, the product of A1 to AN, where each A sub k is a chi by chi complex matrix. Okay, so the dimensions of this matrix, we're going to assume they're all the same, and they're all chi. And here chi will be the bond dimension. And if you like pictures, then this matrix product state admits this tensor network representation, like the one on the screen. Okay, so the one nice thing about having a matrix product state is that the Schmidt rank across any cut is chi. And now maybe you're starting to see how this statement relates to the previous statement about Schmidt number. Okay, but let's keep going. So here's our second statement. Our second theorem says that, again, if we have any inverse temperature beta and any quantum spin chain H, then its Gibbs state can be expressed in the following way. So this is not yet a matrix product state, but we will convert it into one. But let's look at this statement and parse it. So the Gibbs state can be decomposed into operators m1 to mn minus m plus 1. Okay, so maybe just think of this as decomposing it into n operators. It's a bit less, but let's not worry about bookkeeping. And these operators mi have the following property. So each mi is supported only on a few qubits. In particular, each mi is supported on qubits I to m minus 1, where little m is exponential in beta. I'm calling this a few qubits, but few just means it doesn't grow with system size, even though it's quite a lot of qubits. Okay, so the Gibbs state.
Sorry, question B.
Yes.
Is this an approximate statement or an exact statement? Because it's written as an exact statement.
It's an exact statement. Every statement in this talk will be an exact statement unless it will be an algorithm.
Okay.
And algorithms will be approximate because we cannot store real numbers on computers. Yeah. Okay. So each of these operators mi is supported on m qubits. M is exponential in 16 times beta. And you have this like product of operators, and the thing in the middle is actually a convex combination of stabilizer product states. So this operator sigma in the middle, it's separable. And not only is it separable, it's actually a convex combination of stabilizer product states across each qubit. Okay. Nice way to think about this decomposition is that you can take your Gibbs state at any temperature or in with temperature beta greater than 0, and you can write it in the following way. It looks like the staircase, and the staircase is then inverted. Here, the mi's act on qubits 1 to m, and then the next one is shifted over by 1 qubit, and the next one is shifted over by 1 more qubit, and so on. And the thing in the middle, the sigma, is actually just convex combination of stabilizer product states, which here in the diagram are these circles labeled Si. Okay, so this decomposition statement is essentially the strongest statement that we prove in the paper. The statement that I showed you previously about bounding Schmidt number is a corollary of this statement. And I'll give you a matrix product state decomposition that will also be a corollary of the statement. Okay, so let me tell you how to get matrix product state out of this. So one corollary of this statement is that, again, at any inverse temperature beta, the Gibbs state can be exactly decomposed into a convex combination or a mixture where the mixing weights are non-negative. Convex combination of matrix product states. These are these phi sub s's, and each phi sub s has bond dimension, which is doubly exponential in beta. So it's at most exp 16 beta. Okay, and the way to convert our staircase decomposition into a matrix product state is this animation over here. So you do this on the top staircase and on the bottom staircase, and you glue them together. Okay. All right. So there's been a long line of work on approximating 1D Gibbs states with matrix product states and matrix product operators. And it's sort of really well known that these techniques both can be rigorously analyzed and work really well in practice. So one way to view this result is saying that 1D Gibbs states are not only well approximated by mixtures of matrix product states, they're actually exactly mixtures of matrix product states, which might explain why these computational methods work so well. Okay, so there's been a long line of work trying to approximate 1D Gibbs states with these MPSs and MPOs. One drawback of these prior approximations is that all of them degrade with the system size. Okay, so some of them degrade mildly with system size. Some of the other ones degrade quite poorly with system size. Now I'll summarize them for you on the next slide, but all of them do degrade with system size. On the contrary, this statement that I have over here has no dependence on n. So as I said earlier, you could apply this in the thermodynamic limit. You could take n to be infinity if you like. Okay, so let me compare this with all the prior work. This is not all of it. I took a subsample of the prior work so that it could fit in one slide. And I don't expect you to go through all of them, but the thing that I wanted to highlight is that all the approximations here that are global depend on the system size explicitly. So each one of the like bond dimensions over here has a dependence on n. The approximations that are local implicitly depend on system size. So the local approximations just mean that they apply to constant size subsystems of the state, or like the dependences, typically exponential. The one result I'd like to highlight is again the one by Guahara, Alhambra, and Usher from 21, which obtains a sub-exponential dependence on beta. So their dependence on beta is better. We have a doubly exponential dependence on beta, but it incurs this sublinear dependence on n. Okay. So a natural question is, can you get the best of both worlds? Can you get an exponential or sub-exponential dependence on data and also have no dependence on n? And we don't know how to do this. Somehow the analysis techniques that we have all get stuck at this doubly exponential in beta bond dimension. Okay, I'll give you one last theorem statement, and then we'll actually jump into how to obtain such statements. And this statement actually is an approximate statement. So this is an algorithm for preparing 1D Gibbs states. I should point out that all the prior works in the previous slide that I mentioned also yield algorithms for preparing 1D Gibbs states. Since these matrix product operators and states can be implemented efficiently. So do we. It's very similar in spirit. So this algorithm runs doubly exponentially in beta and in polynomial in n1 over epsilon, and it outputs a description of an MPS with the bond dimension, which is doubly exponential in beta. And over the choice of the randomness in the algorithm, if I take the expectation over phi transpose, then I will be close to the Gibbs states in trace systems. In contrast to the previous results, this one has a bond dimension that is independent of system size, but it's actually like a bit slower than the previous algorithms, depending on what beta regime you pick. Yeah, because the previous ones depend only sublinearly. The bond dimension depend only sublinearly on n. There's this really nice recent work of Bergamaschi and Chen, and they obtain a polylog depth quantum algorithm for preparing rho sub beta. I should say that our MPS can be implemented with a depth n circuit. So this is like the naive implementation of the MPS that we output. But I would like to conjecture that the MPS that we output can actually be prepared in logarithmic depth. I don't know how to prove this. It requires proving a couple of new structural properties about our MPS. I'd be happy to chat more about this if anyone's interested, including injectivity. But one would expect that these kinds of conditions are true, and if they are, then you can actually try to prepare something that is close to the Gibbs state with just a depth log n circuit instead of the depth n circuit that would be required to implement this algorithm above. Okay, so that concludes all of the results. And the next part of the talk will be fairly technical, so maybe I'll pause here really quickly in case there are any clarifications or questions. Okay, I guess I should assume that everything is extremely clear, and I'll keep chugging along. Okay, so let's change gears a bit and talk about some of the mathematical tools that go into proving results, like the one that I showed you. Yes.
Ainesh, before you move on, there's actually a question. It was delayed in the chat.
Yes.
Yeah, so the question is from Mateo. So how does the result of Bergamaschi and Chen depend on the temperature?
Yeah, so they don't state the dependence on the temperature explicitly. When I talked to Anthony, he said it's at least W exponential in beta, but I don't know for sure. Yeah. Okay, so let's jump into the technical part of the talk. And the main technical insight that I want to convey to you is this thing that we call an entanglement bulk decomposition. Let me give you the statement and then I'll tell you how to interpret it. Okay, so this entanglement bulk decomposition says the following. It says that, okay, for now, let's just focus on the unnormalized Gibbs state. The normalization is just a constant, so it doesn't matter. And the claim is that the unnormalized Gibbs state can be written as a product of three operators. The first one is this operator M. This is going to be the bulk of the quantum correlations or entanglement. The second one is the Gibbs state on everything but the first qubit. So H sub 1 is all the terms in the Hamiltonian that contain the first qubit. So H minus H1 is the rest of the Hamiltonian. So H minus H1 is only supported on qubits 2 to n. And this operator X, which will end up being separable. Okay, so a bit more precisely, M is supported on the first exponential in beta many sites. The second term, e to the minus beta H minus H1, is the residual Gibbs state on sites 2 to n. And this matrix X is going to be a quasi-local perturbation of the identity. And I'll define what I mean by quasi-local perturbation in just a second. But let me give you a picture. So here the Gibbs state is supported on all n qubits. The decomposition is saying M is this operator that is the bulk operator. It's supported only on qubits 1 to little m. This is some exponential in beta. They have the residual Gibbs state that is supported on all qubits from 2 to n, but not on qubit 1. Okay, and X is this thing that I'm calling a quasi-local perturbation of the identity, but what this will end up being is a separable operator. In particular, it would be a complex combination of stabilizer product states. Okay. So let me actually define this quasi-local perturbation. We'll say an operator X is a quasi-local perturbation of the identity. If X admits a decomposition of the following form, its identity plus a coefficient, so say 0.01 or 0.1 times some operator F1 plus 0.1 squared times some operator F2, so on, where these operators F sub I are supported only on I qubits. Like the Tth operator F sub T is supported on T qubits. Okay, and each one has operator norm at most 1. Okay, so in terms of pictures, this quasi-local perturbation of the identity looks like the following. We have the identity. It's not supported on any qubit. We have 0.1 times F1. It's only supported on the first qubit. The second one is only supported on qubits 1 and 2. F3 is on 1 to 3, and so on. Okay, so this entanglement bulk decomposition is giving us a way to write the Gibbs state, non-normalized Gibbs state, as a product of these three matrices. Okay, so let me quickly say why writing any operator as a quasi-local perturbation of the identity implies separability. It implies that it actually can be written as a convex combination of stabilizer product states, which is a stronger condition than being separable. And this argument is essentially borrowed from this result I had with Alan Liu, Ankur Moitra, and Yuan Zhang about high temperature Gibbs states being separable. This is implicit in that result. And the intuition is the following. It says that the set of separable states is a convex set, and it's centered around the maximum mixed state, which is the identity. If I perturb the maximum mixed state with an arbitrary operator, then the operator norm that I can handle that will make me remain inside the set is 2 to the minus n. This is essentially the result that Gurwitz and Barnum proved in 2003. But if your operator or your perturbation capital delta is L local, it's not an arbitrary perturbation, then this identity plus delta will remain inside this convex set, as long as the operator norm of delta is exponentially small in L, which is the locality instead of N, which would be the case if you had an arbitrary operator. Okay, so that's the very high level intuition for why, like you can actually get something which is independent of system size as long as your operators are local. Like I said, the images here, like on the right, you have this convex set, which is the set of separable states. The maximum mixed state is at the center, and we're trying to understand how big a perturbation can we make in order to stay inside the set. Okay, so that's the intuition. And if you'd like a quick and dirty proof of how to do this, I'm gonna rush through this because I think the other part of the talk is a bit more interesting. But let's do it quickly. So let P be some polystring, and I plus C times P can always be written as a convex combination of stabilizer product states, as long as this constant C in magnitude is at most 1. Okay, and here's an example. So if I had my input being identity plus C times XY, so just sigma X, sigma Y, the Pauli matrices, you can decompose this in the following way into a convex combination of stabilizer product states. And this combination will be convex because C in magnitude is always at most 1, which means this coefficient will be positive and this coefficient will be positive. Or at least non-negative. They could be 0. Okay, and then if you wanted the stronger statement, what you would get, the way you prove this, or like this is an example, but if you want to prove the statement, the way you would do this is you would just write your operator in the stabilizer basis. This is explicit, and we know that the eigenvalues lambda sub s will be either +1 or -1. And again, these coefficients will always be non-negative because the magnitude of C is at most 1. So again, each of these coefficients will be non-negative. They in particular cannot be 0. Okay, so that's the first step. So any operator that is like identity plus a constant times P is a convex combination of stabilizer product states. In order to get the lemma, you take each operator ft above, and you decompose it again into the Pauli basis. So you write it as a sum of Pauli matrices with support size T, the coefficients, which are alpha sub P times the Pauli matrices. Now, it's not that hard to show that these coefficients, alpha sub P, are all going to be bounded by 1 in magnitude. Here's like the quick calculation. Going through it is not super important. You can see that it's very explicit. The last observation then is that we can take this operator, which is one of the terms in this decomposition. It suffices to take one of the terms in the decomposition because I could just sample one term with probability proportional to its coefficients, since these are inducing a probability distribution. This is a well-defined process. So let's say I pick the TS term, and now I have identity plus a coefficient, which is like 0.1 to the T, times Ft. And I want to show that this is separable. And the way I do this is that I can write this as 1 over 4 to the T. This is coming from the fact that there are 4 to the T many Pauli matrices. So when I write any operator in the Pauli decomposition, I can pull out this 1 over 4 to the T outside. And inside I have the sum over the Paulis, identity plus Cp times P. And if you go through this calculation, the magnitude of these coefficients, C sub P, will be less than 1, which is exactly what we needed in the first statement here in order to conclude that it's a convex combination of stabilizer product states. Okay, so that was a rushed proof, but believe me, all the details are not that hard to verify. And it sort of intuitively makes sense. Like if I have this quasi-local perturbation on the identity, I can sample one term and then argue that each such term that I'm sampling is separable. Okay, so let's go back to interpret this entanglement decomposition. we had the product of these three matrices. The first qubit actually, so this decomposition says that the first qubit actually only shares quantum correlations with the first exponentially many qubits, so exponential in beta many qubits, and no more. And the reason for that is that this operator over here does not involve the first qubit anymore. So while there are quantum correlations in this operator, we've removed the influence of the first qubit. And we also argued that since X was a quasi-local perturbation of the identity, X is separable. So there are no quantum correlations here, they're just classical correlations that are left. Okay, so that's why this entanglement bulk decomposition is useful. And maybe you can already see where we're going with this. So this was one step of the decomposition. In order to get the full decomposition, we just take this one step and we recurse. Okay, so we applied it to the first qubit, and now we'll just apply it to the second qubit. This will give us a product of two operators, M1 and M2. And down here, we get X2 and X1, both of which are quasi-local perturbations of the identity. And what we end up proving in the paper, this requires some technical effort, is that the product of them continues to be separable. Okay, but just to see how this argument proceeds, we managed to analyze the quantum correlations that the first qubit is involved in. And then we repeated the argument for the second qubit. We got this picture. Repeated for the third qubit, fourth qubit, and then you're done. Since you've hit the end of the chain, eventually the chain here was just 6 qubits. But yeah, you repeat this n minus m times, and you manage to extract exactly where the quantum correlations are and separate them from the classical correlations. Okay, so this decomposition, if you were paying attention, the left-hand side is now e to the minus beta h over 2. So it's just half of the Gibbs state. And the reason I did that was the following. So if I wanted to apply this decomposition to the entire Gibbs state, here's what I can do. I can write the Gibbs state as e to the minus beta h over 2 times its conjugate transpose, and then apply the previous decomposition to both of them and stick them together, which gives me the staircase, which is then reflected along the x-axis, and you get the separable operators and then these bulk operators. Okay, so that's the full decomposition. So I guess it suffices to prove that the entanglement bulk decomposition is true in order to get the final result that I was claiming. So let's do that. I guess I won't have time to give you the full proof, but I'll at least give you an idea of what goes into proving a statement like this. Okay, so the starting point for proving such a statement is looking at this thing called an Araki expansional. It's essentially the same series that Araki was analyzing when he was looking at these 1D spin chains back in the 60s. And it's the following series. So you look at the operator, which is e to the minus beta h. This is just the Gibbs state. And you multiply it by e to the beta h minus h1. Okay, so this is the inverse of the Gibbs state of the residual Hamiltonian. Okay, so the Hamiltonian you obtain after removing the first site. This is the same operator that appears in the separability paper. So analyzing the series somehow gives us a lot of insight into the entanglement behavior of Gibbs states. And I guess it's perhaps not that surprising. Okay, so this series admits a recursive decomposition. The tth term in the series is beta to the t over t factorial times an operator f sub t, where this f sub t is defined recursively. It has two terms. The first term is the commutator of h with ft minus 1, and the second term is the previous term, so ft minus 1, just multiplied by a single site, which was the operators on a single site, which was h1. Okay, so in this high temperature Gibbs states are separable paper, what we showed was that if you look at the series, and if beta is less than a fixed constant, so it's like less than 1 over c star, where c star is some fixed constant, then the coefficients of this series, in particular the coefficients of each term, decay geometrically. So each one of them is bounded by 0.1 to the t. The 0.1 is arbitrary as long as it's less than 1/4. I think you're fine. And this is precisely the point. This means that this operator itself is separable. Since these coefficients are decaying geometrically, it's actually a quasi-local perturbation of the identity, and we just argued that such perturbations are separable. So the question they have to contend with in analyzing 1D spin chains is that you don't get this property that beta is less than 1 over c star. But you can show that the series in 1D always converges. Okay, so it's not going to be separable. Each coefficient is not going to decay geometrically. What happens instead is that the first few coefficients, in particular the first exponential and beta many coefficients, are going to be super large. They're going to grow very, very quickly. But after exponential in beta many coefficients, they start decaying again. And this is a phenomena that only happens in 1D for this particular series. Okay, so at a very high level, these first few terms are giving us the bulk operators, which are M, and the rest of the terms are giving us this quasi-local perturbation of the identity. And the point is that in 1D, no matter what beta you pick, you can always execute this argument. Beta doesn't have to be smaller than a constant for the series to be convergent in 1D. Okay, in the interest of time, I'm gonna skip this lemma. Or, actually, maybe I can just do it. It's a fun lemma. Okay, so how do you use this Araki expansional in order to get this entanglement bulk decomposition? Whereas here's one lemma that you can prove. You can show that if I look at the product of these two operators, it can be decomposed into this bulk and tail behavior, like I was saying. The bulk behavior is coming from all these coefficients, which are large, but there are only exponential and beta many of them. So in particular, this operator M is supported on the first exponential and beta many sites. It's also well conditioned. Like this operator isn't arbitrary. You can bound both its largest and smallest eigenvalue. And this is bounded by W exponential and beta. And then the tail we can show, since the coefficients are geometrically decaying, is this quasi-local perturbation of the identity. So the matrix E here is just the terms that appear after the first exponential and beta many terms, which have large coefficients. Okay, so how do you use this lemma, which you can prove by analyzing the coefficients? This is like the major technical bulk of the work, and it involves some nice combinatorics. I won't go into that, but I'll tell you how to take this lemma and get the entanglement bulk decomposition out of it. So we have this equality here. All we'll do is we'll right multiply by e to the minus beta h minus h1. There should be a minus here. Sorry for the typo. Okay, so if we do that, this side becomes the identity. We just are left with the unnormalized Gibbs state. And then we have m times I plus e. So m is this bulk part, which is only supported on a few qubits. E is a quasi-local perturbation of the identity. And we have this right multiplication by e to the minus beta h minus h1. Okay, so now we'll do the following trick. We can stick an identity over here between m and I plus e, and rewrite the identity as e to the minus beta h minus h1 times e to the beta h minus h1. These two multiply to give you the identity back. This is just a manipulation. I haven't done anything that interesting yet. But now we'll take this product of operators and just open the product. And expanding out will give us the identity, which is just these two canceling out. And the imaginary time evolution of this quasi-local perturbation of E. So we left and right multiply by this residual Gibbs state. Okay. And I guess like most of the technical part of the paper is showing that this imaginary time evolution of E remains quasi-local. It a priori may not be that obvious because in some sense, this series and this Araki expansion all behave the same way. The first few coefficients are super large, and then they start decaying. And you might be worried that the first few coefficients may completely break quasi-locality, but there's a way to argue that it doesn't, but it involves some careful bookkeeping. Okay, so let me conclude with a summary and some future directions that I'm excited about, and I welcome all of you to think about them. So the main point of this work was that 1D Gibbs states are convex combinations of matrix product states. And this statement is true at any temperature. In particular, it's true at very low temperatures as well. It's just that your bond dimension increases as a function of inverse temperature. So the first question then is that if you wanted an exact statement of this form, do you really need this doubly exponential dependence on the bond dimension? Or can this be improved? Okay. As I alluded to earlier, our MPS implementing it naively requires a circuit depth of n because it is the staircase where each time you shift by 1. But this MPS is explicit, and it should have like injectivity and correlation decay and other nice properties that you might want. So maybe you can prepare it using a log depth quantum circuit. I don't know how to do this. This would be very nice to show. And at least in the case of 1D, we were able to give some insight into what happens below the separability threshold. But it's fairly natural to ask what is going on in this regime in higher dimensions. And somehow the techniques that we have here only work for 1D. And then there's a reason for this, which I guess I'll tell you about now. And the reason is that in 1D, we don't expect there to be long-range quantum correlations or long-range classical correlations at any temperature. So in particular, we can separate out the correlations into these bulk operators that only act on nearby qubits. But in higher D, this is not the case. So even in 2D, we expect there to be non-trivial phase transitions where we have these long-range correlations. So it's not obvious that a statement of this form should be true for any beta greater than 0. But yeah, I don't know how to either prove or disprove such a statement. So in particular, here's a question. In 2D, can you always decompose the state into a mixture of PEPs or any other reasonable tensor network of your choosing? If you did manage to show a statement like this, one consequence of it would be that you would be able to separate long-range correlations into classical and quantum, right? So you would be able to get insight into whether these correlations, like how much of them are quantum correlations and how much of them are just classical correlations. Just in the way that we could for 1D, where the quantum correlations are just these bulk operators, and the rest are quasi-local perturbations of the identity, which in particular are only classical correlations. Okay, I went 1 minute over, so this is a good point to stop. Thank you so much for listening. I can take questions now.
Yeah, so thanks a lot, Ainesh, for the super interesting talk. Yeah, so if, there's some clapping in the audience. So if there are questions from anyone, please do share them in the chat, or maybe also if you want to speak up, I think also Alberto can unmute you. I don't know if you can already do it yourself. Okay, so we have first question in the chat from Isabel. So question is, maybe you said this, but do the MPS in your decomposition belong to any particulars of class? As in, is there any additional structure on the MPS?
Any particular subclass? Well, the most general statement I can make is that it's the first exponential in beta many times of this series that I showed you. That is explicitly what the operator is. So the operator obtained admits like a very explicit description. The only properties of it that we use is that it acts on its support is the first exponentially many in beta qubits, and that it's well conditioned. And we don't use any other properties in the analysis that we have. But the MPS is pretty explicit. So if there are any structural properties of it that you'd like to understand, you could probably just look at it and see if you can analyze it. Yeah.
I think the next comment is, for example, injected MPS, but I think you already said that you don't know if they're injective.
I don't know. Yeah, I haven't managed to show that yet.
Thanks. Okay, so I also have a question. Oh, okay, there's a few from the audience. Okay, so I first say the ones from the audience. So could you comment further on the conjecture about the quantum circuit for preparing the mixture of MPS? What would it look like to prove this, I guess? Do you think it could give us insights on thermalization also? Yeah.
Great question. What would the circuit look like? So our circuit is a staircase. What I would really like is a smaller staircase, just like a logged up staircase, and then you can maybe have overlapping such circuits. If the MPS was injective, this would sort of be what our circuit would look like, because after a few qubits, you could truncate and then restart. Oh, the other question was about thermalization. Yes. So if you manage to prove this injectivity or correlation decay in the MPS, you also get a statement about these 1D Gibbs states thermalizing at any temperature in the style of my co-authors' results. Sun-Won and Zhao have this result on thermalization. And it would go through if you manage to prove correlation decay in our decomposition. Yes. And this is stated in the paper. So you can take a look.
Because another question from Matteo. So could the double exponential dependency on the one dimension on the one dimension temperature be connected to hardness results of ground states?
Right. So indeed, but even if you had a single exponential dependence on the inverse temperature, you would still expect this hardness. So I guess the question is it really doubly exponential, or can you get away with singly exponential? And this question is particularly fine-grained, because if you allow yourself approximations of the kind that Alvaro and his co-authors allowed, where you don't want an exact statement, but you're okay with something that is epsilon close to the Gibbs state, and you can improve the dependence on the inverse temperature all the way to being sub-exponential in beta. So it's sort of a tricky question.
Okay, so I also have a question actually. So it's about the, so you essentially what you prove is that you have a convex combination of MPS. So the algorithm to compute this tensor network will be, I guess, to have to sample from this distribution, the classical distribution, and then compute the corresponding MPS, right?
Yes.
And then, do you know how to sample from this distribution?
Yes, this distribution is just the same distribution as the separability distribution.
Right. So is it also like a Markov chain, or out of curiosity?
If you wanted log 1 over epsilon dependence, then you could view it as a Markov chain, or this tree sampling procedure that we had. If you only want a poly 1 over epsilon dependence, you can just write it down explicitly, truncate it, and sample.
Yeah. So one thing I wonder is whether you could. Right. So I think if you compare this scheme to the way people do algorithms numerically in practice, like these METs, if I understand them correctly, what they do is they sample from a computational string, and then they apply a tensor network approximation to e to the minus beta h over 2, which is different to what you're doing, no? Because you're offloading some of the correlations to the classical sampling. So it seems to me that maybe with your scheme, you could even numerically you could improve what people do in practice. No, you could improve the dependence in the one dimension.
That's a very interesting idea. So I don't know what people do in practice, but just hearing your description of it, we do try to separate the quantum and classical correlation. So we're pushing all the classical correlations into the sampling from this string, like the string of stabilizers. And what this decomposition proves is that all the classical correlations are contained here. So if you have a good sample from this part, the quantum correlation should only be localized. Like it should only be these bulk operators. So yeah, maybe this can help improve
Yeah, I guess
algorithms in practice.
my impression is that my impression is that if you do this in practice, you will have a very good scaling with the one dimension in practice also. So, okay, are there any other questions? Okay, so another question is, do you actually need to work with the global trace norm for the approximation, or you could also consider other notions of closeness?
The approximation in the algorithm.
Sorry, what?
That's like the only approximate statement. So like, is the question about approximation for the algorithm or?
Yeah, I think so. No, if you, I guess you care about the trace norm, and then the question is whether you could consider other notions. Is there anything you thought?
Right. So I guess you could consider any notion of closeness that you love.
Okay, since we're mostly done with the questions and so on, I would suggest that we maybe leave it there, because maybe he will take unless he comes back right now, which doesn't seem so. No, I think we can probably leave it there, right? So,
Yeah, it's like that. So yeah.
Okay, so yeah, I guess if there are any other questions, you can probably send them to Ainesh by email or other means. Yeah, thanks a lot for coming to the seminar.